And you think of Venus being done, and then it would just keep going, and there would just be blood everywhere.
I haven't used it a huge amount of time. Just timing whenever I've got time free or whatever. Now it isn't. Now it isn't. You've taken over there, I think.
What?
Is that you?
That's not right. Someone's put it on you.
Lying down on my knees, I haven't gone off in the afternoon, so I went up late. And next thing you know,
That's why I didn't waste the time.
How would used to please nose on your eyeball to wake you up?
This is usually
Yeah, you know what I used to come up behind people.
Testing the new
You do realise Friday and Saturday.
Yeah.
Testing the new stuff.
I
And it
Well, we'll have a look at it later.
scared a lot of people.
I can't understand what's going on.
It was there.
one time I let us think it was my wife.
Only one?
That's not a touch screen. Well, if it's not a touch screen,
No filters.
they don't want
So from then on, there was a baby gate on the bedroom door.
There wasn't really
It is.
turn that off. Almost just getting that sort of
Did you sleep on very well? Yeah, that's one to school,
Oh, yeah. I better go.
Same colour as honey. Is that colour?
I'm just going to, when they can start coming up with something is that changed?
Yeah, no, it was
Because they
Rescue cemetery. That's the response as a region. Was kept in a
Good evening, everyone. Hello, everyone, and thanks for coming tonight. Just before we get fully started, I'll stand here in front of the entire internet, apparently. All these people who never knew me before now do. They still don't know why. Last week, this is a Lenovo laptop power supply that was left. So if anybody comes across someone who's asking about one from the society or whatever that they may have left behind, let them know that if we don't get any feedback soon that we're going to be leaving it here at the library, because it also might be someone else's property that's been left here at another thing and was just happened to be still here when we were here last week. So I'll just leave that, and welcome to tonight's presentation from Richard, who's going to tell us all about the rather remarkable world of eyepieces, which can be quite fascinating actually.
It can be. You might not feel like that the other night.
And another thing in astronomy that isn't cheap.
Yeah. Okay. So, all right. So welcome everyone. I thought about this because I got interested in bino viewers. And then I started thinking about my eyepieces, and I thought that none of them will fit bino viewers. They're the wrong, because bino viewers are really complicated. You know what bino viewers are? Binocular viewers for your telescope. So, and then I started reading about eyepieces and just got off on a tangent. And
That's unusual.
yeah, as usual, most unusual. Would you stop making those comments? So the long and the short of it is that I decided I'd prepare a talk on eyepieces because I got interested in them. And gosh, there's some very good stuff out there at the moment. There's also some junk eyepieces that you want to avoid, but there's some really, really good stuff for a moderate price too. So what I thought I'd do is, now, quite a few slides here, but I won't be going through all the material, so don't panic. I actually record this for myself because there's some interesting stuff about the history of eyepieces. Which ones came first, how they developed. Basically, as you'll find out, it started with a couple of bits of glass, and then went to 3, and then it went to 5, and we've got up to 8 elements in some eyepieces now that are really expensive. But that's to achieve certain goals, as you'll see. There's no music. No, not for this. Later on. So, what about eyepieces? So, now there's a selection of, I think, Urban Scientific, or one of those, I can't remember which selection there. But anyway, let's have a look at them. So the first thing I'm going to do, these are the topics I'm going to cover. I can see people nodding off already. No, don't, stay awake. The first one, a bit of an introduction. Then we're going to talk about all the things about eyepieces that are important. And in fact, those first 6 or 7 are probably the most important. And then choosing eyepieces, well, that's really up to you. There's so much choice though that's available on the market, but you really only need 3. And if you don't want to spend any more money, get yourself a Barlow, and then you're fixed, basically. Unless it's a really good Barlow, like I tell you, and then you don't need to lash out anymore because you've got a whole set of magnifications. So 3. But anyway, we'll come back to that. I'm not using that shattered mirror that you use. I really like that, Lisa, actually. Sorry. Transitions are really fancy. So what is an eyepiece? Well, there's a nice new one. Explore Scientific have come out with some rather good eyepieces, and they're one of the good manufacturers. I don't know what the purging is, nitrogen purge, you get them binoculars, argon purged. But anyway, an eyepiece is an ocular or a type of lens that is attached to a variety of devices like telescopes and microscopes. It's named that way because it's your eye, it's the eye end that you look through, and the first bit of glass at the top is called the eyepiece, the eye lens. And the second bit, or the bit at the bottom anyway, regardless of what's in between, is called the field lens. So they're really 2 main structural components, and there's other stuff inside them. So it brings, what does it do? It brings light to a focus, because inside your telescope is a tiny point where those rays converge and cross over, and you can't see that, but your eyepiece magnifies it and focuses it for you. And well, strictly speaking, your eye does does that bit too. It has a role to play, obviously, but it magnifies it, and then it gets onto your retina, and your retina does the rest. So what comes out of your eyepiece is a cone of light, which your eye handles. So there's a demonstration of what we're talking about there. So you see that that crossover point there. Oh God, I can't see anything. Right there at that point there. So that's a focal plane for the telescope, and then the rays cross over and go through the diagonal, and they're focused, and you're able to adjust that for your eyes. It's really rare for someone not to get something in focus in a telescope, because telescopes got so much range in them. You know that yourself when you're wrecking them out, a huge amount of movement. So regardless of how good or bad your eyes are, you're looking doubtful there, Brian. You should be able to bring things to focus. Anyway, so this is in a Newtonian telescope in the mirror. The same concept applies. It's going to have a focal plane, but of course you're looking at a different part there. The eyepiece is not located at the end; it's located on the side. Now, so here are the parts. So this was a Ramsden really early eyepiece. So it's actually got 2 pieces. Looks like it's got 3. The middle bit doesn't count. So you've got a plano. You know that plano means flat, convex bulging out. So it's got two planar convex lenses and they face each other. So the top bit is flat. Let me just see if this works. No, sorry. It's a very lazy sort of thing. No, I didn't mean to do that. Sorry, back we go. Anyway, so you've got these two bits, and the field stop is the bit of the barrel that closes up, gives you a nice edge to what you're looking through. Okay, that's important. So they're the three main parts. Now you might have a whole chunk of glass in between, all sorts of things, but basically that's it. The eyepiece end, the eye end, the eye lens, and then the field lens at the other end. And this is a very short focal length eyepiece. It doesn't look like it, does it? This is a 3.5mm eyepiece, but look where the field lens is here. It's right near the end. Now, in some eyepieces, you've got to look really well deep inside to find it, depending on the structure of the eyepiece. But that's right near the end of it. So I never use this. It sits at home. Too much magnification. So anyway, I'll get on to that topic shortly. So contrary to many people's expectations, the eyepiece does not produce an image. Right? It just converts the conical beam of radiation from the telescope objective into a parallel beam, and the eye then focuses the beam on the retina. So the eyepiece does the focus, helps you to focus, but your retina is where you, and of course it's going to be upside down in the retina, isn't it? Usually. To make matters more confusing. Anyway, so any questions about that? So eye lens, field lens are the two main bits, and then there's stuff in between. Now, so characteristics of the eyepiece, continuing. First one, focal length. Now, the focal length of an eyepiece, by the way, is written on the barrel. So the focal length is the same concept as in a telescope. The distance required to bring that, if you hold that up, the focal length of that between the first lens and the optical centre is 14mm. So that's pretty short, very short. So compared to the eyepiece I just showed you, which is extremely short, this is what we call a medium eyepiece. This is a 14. So, oh, thank you. Thanks, man. So, now let's talk about focal length. So you've got focal length in eyepieces and you've got focal length in your telescope. And you're adding the two together to create that image that you look through. Focal length is the distance measured through the telescope's primary lens or mirror and the point at which the light rays converge into that point I showed you, that crossover point. It applies to all telescopes and eyepieces, the distance between the lens and mirror and the point at which the lens or mirror forms a focused image. Now the focal length of an eyepiece is a distance from the plane of the eyepiece where parallel rays of light converge to a focal point. So inside that eyepiece, it's got its own focal length. Every eyepiece magnifies what you see regardless of the type of telescope. And that magnification, how do you get magnification? Magnification is the focal length of your telescope divided by the focal length of the eyepiece. So let's take, what's this one? We'll take an easy number, like 10. This is a 10mm eyepiece, right? So say my telescope is 700 millimetres long, which it is, my short refractor. 10 into 70 goes, 700 goes 70. So I get 70 magnifications from that eyepiece. So if I use a 5mm eyepiece, obviously I'll get double that. I'll get 140. And so on. Does that make sense to everybody? So that number divided into the focal length of your telescope. So what does this tell you? The longer the telescope, the focal length of the telescope, the more power you have. But there are complications with that, as we'll see. So there are trade-offs with everything in this hobby. That's one thing you discover. At the other end, you've got a very low power eyepiece. This is my favourite eyepiece, which is not a Pentax at all. This is a Bada Hyperion aspherical eyepiece. This is a 31mm eyepiece. So 31 into 70 gives me about 22 magnifications. So I use this for thanks, Stephen, very good, well fielded. This is the best eyepiece to use for looking at nebulae and things. It's beautiful. It's so bright. And we'll come to the reason for that too shortly when we talk about a bit more about eyepiece characteristics. So there's that formula. So if you've got a telescope that's 1200, like my big Bertha, that's 1200, and you use a 20mm eyepiece, which is down here somewhere, 20mm, bung that into a big berth at the end of the diagonal, the mirror at the end, I get 60 magnifications. Everyone understand the math? Pretty straightforward? Yep. So that has important ramifications for what you're going to look at and which eyepieces to use for which kind of things you look at. That's important. So let's move on. Oh, Vixens. Steve has very kindly bought his Vixens, which are beautiful eyepieces along here. And you've got a different set from mine, haven't you, Steve? Yours are LVW. Oh, this is LVW.
Yeah, they're the same. They're the same.
Same, yeah. This is a 42. This is extremely, this is really wide field. Now, another thing I'll talk about is why you have to have a big eyepiece when you're doing wide field. Some wide fields you can't get in 1 1/4 inch. You can only get in this size. And that's because but now they've introduced, Teleview have introduced 1 1/4 inch eyepieces with massive fields. Explore Scientific as well, down as low as you'll see, 5 and 6 millimetres. But they cost an arm and a leg because of the optical acrobatics involved in giving a wide field. But this gives you a wide field anyway. 42 into Big Bertha 1200 is about 30 magnifications, a bit less. So you can see that's pretty low power, but beautiful, really bright. In fact, I could swear when I look through this thing, the sky looks blue, not black. I don't know whether it's just
I get that.
Yeah, it's odd. It isn't pitch black.
Because it's much lighter.
Yeah. Any light that's around it scatters, obviously, so you don't actually get the contrast you think you might get because of the low magnification. Sorry?
Going to higher power, you increase it.
Yeah, that's all we're going to. Yep, that's coming up. Okay, that's just a final. A focal length is written on the barrel, so remember that when you look at eyepieces. So, what happened there? Something didn't turn up. Oh yeah. So, as we said, huge range of focal lengths of different sizes. Anyone got any Nikon eyepieces? I heard one sold for $2,000 something. Guy's got one for $2,000.
That was why we don't have any.
Yeah, they are very, the really good ones are very rare. But these are all cameramen. Pentax, Nikon make cameras, so they've got that history, I guess. So I wouldn't be surprised if they cost it.
So the Nikons aren't any better. So the
some are.
Reflective of the cost.
No, some would be. I think you get what you pay for in this hobby in a lot of cases. But you can always find gems, really good value for money lenses, eyepieces and telescopes as well.
But everybody's always a different too, so...
Yeah, exactly.
What's good for some isn't
Now I'm going to talk about, we'll come to that shortly. The longer the focal length, the lower the magnification. We all know that. Sorry.
Just before you move on, I said that the second one is the 17.5mm one, but that's a strange looking...
Oh, that thing's like a guard to guard light out or something on one side. Some of them have a rubber cup. Yeah, so any stray light. Then you get the other kind, which is just a rubber cup.
Yes.
And that's so you don't poke your eye out, and it kind of brings it down and reduces light all around the eyepiece. So they're all right. They're not a bad idea. So anyway. So, shorter focal length eyepiece, lower number on the barrel of the eyepiece, higher magnification, bigger number on the eyepiece, lower magnification, if that makes sense to everybody. Okay, let's move on. That's the important thing to get there. Oh, there's just an explanation of what those eyepieces are. So, this is from a guy called Gert Valosek, who's got an interesting little website, which I enjoyed reading, and he talks about his selection of eyepieces. He says for very low, like 10 to 20 magnifications, he looks for objects, tries to find where they are in the sky, like a pair of binoculars, I guess. Same concept. Large area nebulae, Andromeda Galaxy, and so on. Low 30 to 50, star clusters, galaxies, and nebulae. Why would you say galaxies? That still seems very low, but the advantage of a lower power is it's brighter. The contrast is better. So you do actually get, you can see bright specks, you can find them, and then if you want to, you can swap to a higher power. So it's quite handy to find things. Medium, craters and valleys on the moon, Saturn's rings, Jupiter and the moon. So now, I noticed Steve's bought an orthoscopic We'll be talking about orthoscopics because they are fantastic at high power. They're really good eyepieces for that. And a high power, in practice, he talks about this, he's got a little heritage telescope, not really practical for that, but yes, certainly for looking at double stars and things like that, separating stars. That's where it's handy to have a higher power or higher magnification. The dimming of an image during magnification is a well-known characteristic of the inverse square law. Now, the inverse square law, let's have a look at a couple of things. Here, I'll talk about this in a moment, this law. If you look over here, here's a different sort of, you're looking at the Orion Nebula. On the left, you've got a lower power. On the right, you've got a higher power. So if you increase the magnification, the image gets larger, but it gets dimmer. And that is because you are spreading the light over a larger area. Now, I wanted to demonstrate this over here, which I will shortly. So it's a really important concept. So we all get disappointed when we we look at, say, Orion, and you put on a higher powered eyepiece, say a 5mm eyepiece on my 700mm telescope will give you, 140 magnifications. And suddenly you can see, you might see the trapezium and the stars in the middle, but it's not as bright and punchy. Whereas if I put the Barter on, I can see the whole thing and it looks glorious and bright, like looking through a pair of binoculars, in fact. So, so that's but bigger. So, so there's always a trade-off. Magnification makes it bigger and dimmer. Does that make sense to everybody? Now I'm going to demonstrate this by looking at, that's just the thing about light, we've already covered that. Another effect of magnification comes into effect when you've got poor seeing conditions. So these GIFs aren't working, but this is from, who's the guy? I'm trying to think of his name. No, I'm just trying to think, I've forgotten his name. Yeah, anyway. So Jupiter under good seeing, one of the writers, one of the famous photographers, so he's taken a picture of Jupiter under good conditions and under lousy conditions. And we've seen people who've taken videos here. You can see how when a planet starts shimmering like it's going through like a mirage, and then it's bad seeing conditions and not worth doing any photography. And you also get that effect low down the horizon, and you get interference, refraction of light through the atmosphere, pollution, a denser atmosphere, because when you're looking that way, you're looking through more atmosphere than when you're looking straight up. Does that make sense to everybody? If you think about that, if you're looking horizontally, you're looking through more atmosphere than when you are when you're looking straight up, because you're looking through the sky. You're not looking. It's not a tangent. It's not a direct 90-degree upwards look. So there's all this pea soup in the way, and other stuff. I mean, not pea soup, but obviously smoke and light scattering and so on. So you have to watch out for that sort of those seeing conditions, and they affect. So when you magnify the bad seeing. So if you've got Jupiter looking in Technicolor, looking the wrong colours and shimmering, and then you magnify it, it's going to look really bad. So, all right. Has this moved? Oh, here we go. Oh, back. Sorry. Let's go back one. I wanted to show this, the inverse square law. Now, this is the concept of the inverse square law. So here I am. Can you all see that? So I'm assuming I'm not really, I'm only cheap though, so I'm a metre from that picture. Now, if I move this back the same distance again, so what happens? I'll try and do that. You can see, oops, roughly. What's it doing? So I've doubled the distance. So now 1/4 of the light is falling on that. Everyone follow that idea? So the square of the distance. So 1 over the square of the distance, the inverse square law says. So if you double the distance, you get 4 times less. If you triple the distance, you get 1/9 the amount of light falling on. Now, because this is a concentrated beam of light from this projector, you can't really see it. But you can see it in a room. You know what it's like. The further away you get this concentrated colour suddenly dissipates and gets lighter and lighter and lighter. And that is what a magnifying through an eyepiece does. So when you magnify through an eyepiece, you're spreading that light over a bigger and bigger area until eventually it looks darn dim. Now that law applies to everything: sound, light, lots of physical properties, gravitation, electrostatics, light, radiation. The law is the same for all of those. So, and also I think for my radiator at home. You know, you're sitting on a cold night and the inverse square law applies. If you move 2 metres, if you move 3 metres, you seem to be feeling a lot less warmth, direct warmth from the heater. If it's a strip heater or something, you know. Well, it's a similar concept anyway. Not quite the same, but anyway, so the intensity of whatever it is, whatever form of radiation, might be light, might be something else, is proportional to 1 over the square of the distance, if that makes sense to you. So every time you double the distance, you get nothing. You get 1/4 the light, 1/9 if it's 3 times the difference, so on. So it's just a square. I might turn that off now. Demonstration over. Fancy.
I thought you were going to project eyepieces through it to show the different fields of view.
Oh no, I'll come to that, but I won't do anything fancy like that. I'm not much of a showman, really.
Yes, you're quite correct.
Okay, would you stop it? Okay. Anyways, so let's leave that because I think that's pretty straightforward. I wasn't going to read the whole thing and I had no intention of doing so. That last one seemed to have frozen a bit. I think I went berserk with all the animations. So there is such a thing as maximum useful magnification. Golden rule: 50 times. I'll come to that in a minute. Look, if you look, there's 50 times the aperture of your telescope in inches. So if you've got a 4-inch telescope, 200 magnification is the most you should use, practically. I actually think it's less than that because seeing conditions, as we just talked about, will interfere with that anyway. But 200, for example, if you have a telescope with a 200 millimeter aperture, 8-inch, like a Schmidt-Cassegrain, a lot of you got Schmidt-Cassegrains, maximum useful magnification is 400. 8 times 5 is 400. 8 inches times 50. Sorry, not 5.
I've only had 1 or 2 nights this year.
Yeah.
We could go back.
Exactly. So seeing conditions don't really, I would say bank on 30 as an average down here, 30 times rather than 50 times. But anyway, if your telescope is a focal length of 2000, you can use up to a 5 millimeter eyepiece, which is this one. So bung one of these in, but you get, you're still going to have problems. It's still going to magnify a lot, and you're going to have a dimmer image. 400 magnifications is an awful lot.
When it's a clear night, when you get that very still clear night, 1 or 2 a year,
Yeah.
you go, wow.
Yeah. I can remember
That's only
looking
1 or 2 a year.
one night, Stephen, we were out at Mount Pleasant. I had Big Bertha there, and I put the 5mm eyepiece on, and that gave me 240 magnifications, and it blew my socks off. It was amazing. It was just crisp, and then it was gone. Which is always just like you think, was that a mirage? Did I see? I have never seen Jupiter through my big telescope because I had trouble with tracking and stuff. And at one time it flashed through. I was focused, and I saw this thing. I thought, wow, and gone. Never got it back. So, but now with all the gear I bought, I hope to be able to be tracking things for long amounts of time. Anyway,
so I think we could see the shadow of a moon on Jupiter through the eyepiece.
Yeah. Oh yeah, that big telescope of mine, that's astonishing when you look at the moon through it. Takes your breath away because you've got the longer magnification and beautiful optics, so it makes a difference. So compared to my little one, which is, the moon's small. So when atmospheric seeing is poor, turbulent air will blur the view and you won't get those great views that you hope to get. Here it is, a little movie. Look, that's poor. That's better. Still moving around, but it's better seeing than the one on the left. So, Damien Peach, that's what I was trying to think of before. Also provide those things, Damien Peach. Okay, so start observing with your longest focal length eyepiece, and then work your way up to get high magnifications depending on the seeing conditions. So it's just experiment basically until you find the ideal thing. the ideal eyepiece to use on the night. Now, field of view, number 2. Am I going fast enough? Am I going too fast? Okay, field of view. I'll speed up a bit. I can see some heads nodding off. Field of view. Now, let me explain field of view. So, if I take this off, and hold that like that, the field of view is what you see through there. It's not the field of view through the telescope. The apparent field of view is what you get with these eyepieces. Now, manufacturers aren't exactly accurate about what their eyepieces do. 40 to 50 degrees was a commonplace field of view for most eyepieces in modern times, but now they've gone up to, this is 70 degrees. There are 80 degrees, 82 degrees, there's 100 degrees, and now there's 120 degrees.
You have to turn your head.
Yeah, now brings a problem called kidney beating, which I'll talk about later. But anyway, so you get this, you get these, you can see, so it might say 70 degrees, but that's just the angle of that can see. Okay, now think about it. A human eye with peripheral vision is about 100 degrees maximum. But if you're older, it's going to be a bit less than that. So you're going to get a bit of wasted. It's wasted anyway.
That's peripheral vision with 2 eyes.
Yes, with 2 eyes. Yeah, it's going to be.
That's 65.
I was going to say, if you look through, if you buy a camera lens, it'll say a normal, 50mm lens, 50mm is 47, 50 degrees, something like that. That approximates what you see. If you're looking at something in daytime, without looking too much at the periphery, you're going to have a good field of view of 50 degrees, say. And the eyepieces originally were around that. So now we're getting into the fields where they're really wide, and you question whether it's worthwhile. So if you see, when you buy one of these, the field of view is just the native field of view of the eyepiece. It's not the field of view you'll get when you put this in the telescope. That's entirely different. And that's what I'm going to show you. So don't get the two mixed up. So AFOV is apparent field of view, which is what that gives. And then true field of view is what it gives when it's inside the telescope, which is a lot less. A heck of a lot less. So let's have a look at that. So the apparent field of view is how wide, I'll skip over, won't read all of this, how wide the eyepiece's field of view is when observing through it, okay, without the telescope, Most eyepieces have an apparent field of view of 40 to 50, but some can be purchased with 100 or more. An eyepiece at the least expensive end of the scale would have an apparent field of view of 35 to 45, whereas the ones that cost, have 100 degrees might be $600. Teleview have some for like that, $600 US, $700. They're really, really expensive. And you wonder what the value is of a wide field, other than a supposed 3D space effect, which there's the same invocation. But bottom one, top one is a wide angle, bottom one is a normal field of view. So, what do you get? Thank you, a bit of water in the desert. Talking too much. If you look, they're the same size, but because of you see more space around the wide angle field of view. So this is probably, that could be a 100-degree field of view eyepiece, generating, it still might be a 10 mil eyepiece, say, with a 100-degree field of view. This is a 10 mil eyepiece that's normal. Does that make sense? Used on the same telescope. So one's same magnification, but very different field of view. Thank you very much. Same view. Right. Let's get going. So, apparent field of view is the angular measure to describe how much of the sky we see when looking through the eyepiece when it's not attached and so on. Now, example, a manufacturer states that a Plossils come with when you buy a telescope, you usually have a couple of Plossil eyepieces, a 25 and a 10 or something like that. So, a Plossil eyepiece has a 25, so it's got 25 written on the barrel, and a 50-degree field of view. It's apparent field of view and not the field of view where you have it in the eyepiece, which is a true field. Now I'm going to show you how to calculate that. True field of view is the apparent field of view divided by the magnification. So I've got my 700mm focal length telescope. I put my 10mm eyepiece into it, my Pentax 10, which has got a 70-degree field of view. I get 70 magnifications. Coincidentally, 70 magnifications, 70-degree field of view. Divide the 70 by the 70, 1 degree. So the field of view is 1 degree. Man, is that different from 70? You know, so you can see it's different to talk about the apparent field of view of an eyepiece and the actual thing you see. But so the true field of view might only be 1 degree in that situation. If I use the APM, that's 1200, put the 10mm eyepiece in it. So I've got a 70-degree, what's that, how many passions? 10 to...
not quite
10 into is 120. 120, that's right. 120 divided by 70 is not quite 2, because that'd be 140. So 1.8 degrees, which is quite wide. I mean, photographically, my camera's 2 degrees. That's quite a chunk of sky still. The moon is half a degree. It's 30 arc minutes. So 4 moon diameters across in your field of view. So it can make a difference. So, you know, the apparent, if you had a 100-degree apparent field of view, you'd have the same magnifications, but you have all the sky around it, which some people love, because you can see, it puts things in context. But you're paying an awful lot of money for that, and you wonder whether it's just right. Yeah.
One area that people go on about is very wide field, the low contrast stuff with a short focal length telescope and a big wide field.
Oh, right.
Yeah. But you need really good dark skies to see these low contrast stuff anyway.
Yeah, yeah.
And the other advantage is planets, if they're drifting around and you don't have a tracking going.
Yeah. This business about, you know how people talk about fast lenses and fast telescopes? And what they're talking about is, if something's a short focal length, it's not collecting any different amount of light from something that's, you know, much longer, and like an F10 and an F5. They will collect the same amount of light. There is no difference, except that the F5 is going to focus that light into a tighter beam over a shorter distance, so it looks brighter. Does that make sense? But it's still the same amount of light, but it's more efficient at focusing that light quickly. Per unit, I don't know how you would consider it, what way of putting it, but and that's the difference. So that's why some
Just
people,
like when you're moving, when you're going from an F7 to an F6 to an F5 telescope,
yeah,
it's like opening up or closing down the iris of the
yeah,
camera lens.
and you've got exactly the same thing. So you let more light in, but it's really the amount of light that's hitting that surface is the same regardless. It's just the optical configuration that focuses it.
For the same aperture, the longer the focal distance is, the bigger the objective has to be.
Yeah, yeah, yes. Oh, we're going to talk about that too. I'm coming to that. You know, if this shows up, you know. So, field of view for stargazers, naked eye, 100 degrees. Well, that's what they say with both eyes, as Steve was saying, and peripheral vision like an eagle. If you're lucky. You know, have you noticed how Stellarium and all these apps they open they've got about 90 to 100 degrees. I noticed one of mine, Sky, I forget what it's called. I don't use it anymore. But that always default screen was 120 degrees. So it's not realistic. You wouldn't see that if you were looking at the night sky. You couldn't with a naked eye. But anyway, a pair of binoculars, 5 to 8 degrees. Spotting scope, much narrower. A low power telescope, half a degree to the moon width, 30 arc minutes. So it's the same thing. A high power telescope, boy, a 10 arc, we're talking about 10 arc minutes, so that's 3 times smaller. Yeah. That, not that one, I'll show you a website later on, which will really blow your mind. Venus may appear as large as 1.5 arc minutes, a full moon, half a degree or 30 arc minutes, and Orion's belt is about 2.7 degrees long. So I couldn't fit Alnitak, Alnilam and Mintaka in the belt into my, no, it's still wider. So it gives you an idea of proportion anyway.
Jupiter is 50 arc seconds.
50 arcseconds, there you go, for Jupiter.
Bit more like
Yeah. Okay, so there's Andromeda. Look, 1/2 degree, 1 degree, that gives you an idea of scale. So anyway, we've already gone through that, so we don't need to explain that. So same apparent field of view, different magnification from different eyepieces. These are really expensive teleview ethos eyepieces, which are the super wide angle ones that have come out with. So the 21mm will give you a different magnification, obviously, from the 13, but they'll have the same 100 degree field. So it just depends on what you want. I wouldn't, they're a lot of money. For eyepieces of a given design, the width of the field of view is generally inversely proportional to the magnification. That means doubling the magnification cuts the field in half. You get a skinnier point of view type field. So there's a good example. Same object, Pleiades, seen at a 50 degree field, a 68 degree field, and an 82 degree field. So, yeah. It doesn't look like the same size, but they are. So true field of view with a 1000mm focal length telescope, and the eyepieces, one eyepiece, 24mm. So that gives you how many magnifications? 24 into 1000, which is about 20 something. What is that? 50? No, a bit less, 40 something. 46 maybe, something like that. But anyway, the apparent field of 50, 68, and so you go, yeah, so 50 into, that's what you can do the math. I'm not going to do the math to work out the actual field, but so each eyepiece gives the same magnification, or the eyepiece gives magnification, but the eyepieces with a larger apparent field of view show a larger angular area of sky. Okay, so there's the same concept again. Now look, on the right is the moon through a very wide, 82 degrees. So same size, but you see a lot more sky around it. I think it's aesthetic rather than anything else. And you're paying a lot of money for the aesthetics. Right? That's just a diagram showing what field of view is. And here's an example of, now Ross, your C8, your Edge HD, with my Pentax 10, looking through it. And that's the tarantula, and that's what you'd see at 203 magnifications. But down the bottom is my little 4-inch William Optics with the same eyepiece in it, and that gives me about 70 magnifications. So that's the difference, 3 times the magnification from one to the other. But which view would be brighter through your telescope? An interesting question, because you've got a telescope that collects more light, so you can probably compensate for that. But then if you magnify, you're spreading the light thinly, and you might not get the quality view that you might get with a wider field with a low powered eyepiece. An eyepiece that gives you a wider field. Sorry?
No wonder I'm confused. Like,
yeah, well, you've got to. What you've got to do, I reckon the golden rule, Ron, is to experiment and have it maybe 3 eyepieces and just see which looks best to suit you.
Also, which is working best on that night.
Yeah, and with that particular telescope, because they do make the boy, they vary. Good, we're only up to 3. Good grief, let's move on. Exopupil. So, in short, the exopupil is the beam of light that comes out of the telescope, the cone of light out of the eyepiece that hits your eye. Your pupil can only dilate, I'll summarise this quickly, your pupil can only dilate if you're young, 7 millimetres. If you're old, forget it. No, if you're old, maybe 5. And so the cone of light that comes out of the eyepiece doesn't need to be 7, and in fact it's a waste of space. Well, it's a waste of light if it's too wider than the pupil of your eye, because the light is hitting your, what's that area, iris and other things. It's not going. Your eye is physically blocking some of the light. Now this effect is called kidney beating, by the way. I'll talk about it shortly, because kidney beating is a real problem. People complain about some of the teleview eyepieces producing severe kidney beating. And they tried to rearrange it, which is losing part of the image because it's so wide field. Your eye's searching, and when you're searching, the pupil of your eye is moving across and therefore blocking out Your eye is actually blocking the light out from one side of the eyepiece or the other. Does that make sense? So you're kind of creating your own curtain effect when you're looking through it. Yeah, a bit disconcerting. So there you go. How do you work it out? Pair of binoculars, 7 by 50. 50 mils the aperture binocular, 7x, 7 times 7. Divide aperture by magnification, and you'll get the pupil. So a 7 by 50 pair of binoculars is very bright. So 7 into 50 goes 7. So you've got quite a big pupil, exopupil. So the light exiting the eyepiece should fit inside your dark adapted pupil. That means you don't come out of a bright room. It's to wait a while. But so 3 mils fine, because it's going to hit. It's going to go right into your, anything between 1 and 3 millimeters is going to go into your pupil properly and not be lost. The light won't be wasted, as we were just talking. As we age, indeed, the pupil size decreases. Rule of thumb: persons younger than 40, like 7 millimetre, older people 4 to 6. And then it says magnifications that produce exopupils that are larger than 4 or 5 are not recommended. And you can do that, as I said, by dividing here we go, magnifications. Exopupil is telescope aperture divided by magnification. That's one formula. Telescope aperture, 100 millimeters magnification. If I've got 70, if I've got my 10 mm eyepiece in my telescope, so 10 into do that again. 100 millimeters divided by 70 gives me 1.5 degrees, 1.5 millimeters exopupil. This makes sense? So it's another little formula. If you forget this, don't worry about it. If you can see things properly, you've got a nice exopupil, and that's all that matters really, regardless of the math behind it. 8 millimeters is bad, and here's the other formula. So focal length of the eyepiece divided by the focal ratio of the telescope. So 10 mm eyepiece divided by my focal ratio of my telescope is 6.9, near enough to 7. So 10 divided by 6.9 gives me 1 point. Back again where we were, 1.5. Same calculation, just different formula. Does that make sense to everybody? But I wouldn't be running around with a list of exopupil sizes, but don't worry about that. It's just a demonstration of a physical property that you need to be aware of when you're looking. People come up to eyepiece and say, "Can't see a thing." Well, A, they might have come out of a bright room. B, when they do look through it, they're not. If they are dark adapted, positioning your eyes so that you actually get that kind of light going to your pupil is a different matter altogether. I'll never forget the night we were at Rosetta Primary, and there were all these kids running around, and they saying they couldn't, looking through our telescopes, couldn't see a thing, and they had LED lights around their necks and everything. Their pupils had shrunk away to nothing. Can't see anything, So that was quite funny. Anyway,
a lot of people ask, should I take my glasses off? And I don't know what to tell them.
I would say experiment, because the massive range of focal range in a telescope is quite prodigious. My APM goes back 240 millimetres. That's an enormous amount of back focus. You'd have to have catastrophically bad eyes not to be able to focus within that range somewhere with an eyepiece. But mind you, you've got to take into account the focal length of the eyepiece. It's not going to focus through the whole range. It'll be able to focus. It's got its own focal length.
I've never had to take mine off.
If your eyes are that bad, you have glasses on.
I just leave them on.
And that sets your eyes for infinity, which is about the same as the focus on your telescope is about the same as someone with good eyes.
Yep. At the moment, I'm wearing my infinity glasses. I had my optometrist make these because I was sick of looking at two moons every time I looked up at the sky. And I put these on. It was better than having a telescope. Just amazing. Just so good. I don't know how I did without them. So when I look at the night sky now, often I just put these on. Just beautiful.
Sell all your gear.
Sorry?
Sell all your gear.
Sell all the gear. I don't do anything else. All right. Sorry. Let's speed up because we've got it. What's the time? Good grief. Okay. I'll skip through these. Eye relief. Eye relief is how close you can bring your eye to the eyepiece and see something.
See this field stop.
Yeah. So the field stop's that thing that blocks the light. It gives you that nice circle. So here we go. Does that make sense to everybody? Just a little diagram. That's eye relief. Long eye relief is a desirable thing. Short eye relief, you bring your eye right up to the eyepiece. Now, this is a product of high magnification, by the way. So if you've got a short focal length eyepiece and you're magnifying, you're going to bring your eye really close to the eyepiece, and you might not see anything. You've got to get your eye right in the right spot and to get that little extra pupil. Sorry.
It's a function of the design of the eyepiece, not the focal length, because you can get focal length for eyepieces of any focal length, the same eye relief.
Yeah, I notice it varies, it does, but generally if you have long focal length eyepieces, you get better eye relief than you do with shorter ones. That's a general rule.
There was a set of eyepieces, the radiant eyepieces.
Oh yes,
ran about 20 mil back
20 mil eye relief, yeah, well that's probably the max.
Through all their magnifications.
Good. Now, that brings me to another, I'm going to talk about that too. We're going to talk about parfocal eyepieces in a minute. I'll explain that to you in a moment, which is related to this in a way. So, anyway, some eyepieces, especially longer focal, have a very long eye relief that makes it tricky to position your eye to get the entire field of view. In general, for eyepieces of the same design, eye relief increases in proportion to focal length, as a general rule. So eye relief of 15 to 20 is ideal. So does it make sense to everybody? So 15 to 20 millimetres above the eye lens, the first bit of glass you encounter, is probably a good position to have somewhere in there. Yeah. All right, so now, the kidney bean effect. Remember I mentioned the kidney bean? So this is the kidney bean at work through a diagram. You can see you've got your eye down, you've got this, there's the focal plane. It occurs when the exit pupil is very large, like say we're talking about 8 millimetres. Can you see that?
No, you're right.
Small, speaking
We're
which,
walking
the
on
diagram is small. So what happens here is, you've got, you have to, if you've got a big beam of light coming out, bigger than the size of your pupil, and you're shifting your eye around to see what's in there, you're going to cut off some of the light. And it's between the centre and the edge. It's midway where the kidney bean is the worst, has the worst effect. And you get a curtain, so you get a blackout. So that's not an ideal. Looking at the edges of your field, your pupil cuts off because the cone of light, the light's going in, instead of going to your pupil, it's going into your cornea, into your iris, because you're blocking it out. It's like drawing a curtain, so you look left and right. I remember Steve was always saying, look around the eyepiece. I thought of kidney when we're doing observing, and it's a good point. If you get this kidney bean effect, it'd be pretty disconcerting. So, kidney bean effect. They have long eye relief, meaning you have to position your eye further back. When you try to move your eye closer to the eyepiece in order to see the edge of the field, parts of it are cut off because of the converging light beam. It doesn't hit the pupil. It goes elsewhere, outside. Yeah. Just quickly, barrel size. I'm going to summarise this in a couple of lines. A lot of these things here, the barrel size is just the width of that. That's a 1 1/4 inch eyepiece. If you've got a telescope like I did about 30 years ago, the eyepieces were tiny. They were called 0.96 or something of an inch. And you can still get them with cheapy, avoid. Never buy those rubbishy little things. Not all of them are bad, they're just small. And I got my telescope from Asbestos. And I can remember I was 14 and I went back to him, Jeff Bester, a lovely fellow, and I said, excuse me, I said, I can't see anything through this telescope. And he said, what eyepiece were you using? And I think I had a 4mm orthoscopic or one of those. And it was, the magnification was really high, narrow field, I couldn't see a thing. And I kept looking around the sky. And I was looking around the sky, I said, that doesn't work. He said, it works, you've just used the low power. I didn't know anything about it then, so the hobby, but so anyway, so these are 1 1/4. This is a 2 inch. Now, when you get a 2 inch barrel, you're not collecting more light, you're not going to get a brighter image from it. It doesn't work that way, because the critical thing is your telescope focal ratio for that, so not the width of the barrel of the eyepiece. But you get the wider field of view. These usually come with a wider. Otherwise, the field stop would be in the way. That bit of thing that blocks off the light and gives you a nice edge. And you can't have a field stop. With these eyepieces, you've got to have a bigger field stop. So, in fact, if you look at this, look how big that is. The glass in the end of that. You can't even see the field stop. But in other eyepieces, the field stop is really, really noticeable. Like on this one. Well, there's your field stop. Look how small that is by comparison. You know, so yeah. Anyway, so yeah, you don't get any more magnification or anything else. It's just a field of view, apparent field of view is bigger and bigger eyepieces. So I used to think they were wonderful when I buy 2 inches. It's a waste of time, and they weigh a ton. I mean, this one doesn't weigh a ton, but if you get something with a 100-degree field of view and it's a 2-inch eyepiece, it's going to be like a hand grenade. It's going to be, and they weigh 500, 600, up to a kilo. Some eyepieces. Imagine that on the end of the draw tube of your telescope. It's going to be putting extra weight on it. And if you've got a small telescope, it'll be too big. It'll cause flexure, so it'll cause your tube to, do that. Not a good desirable situation.
One annoying thing: microscopes have a different barrel size.
Oh, do they?
So you can't use a microscope eyepiece without hacking it out to 1 1/4.
Yeah. Anyway, Nagler, famous.
What's the size of a microscope? What size is it?
Probably.
I can't remember off the top of my
I'll
head.
bet it's close to that 1 inch size.
Yeah,
Not
not
one
inch
inch and a
size,
quarter.
or not 1 1/4.
No,
not 1
less.
1/2.
Something different.
It's annoying.
By the way, when you see Nagler, Al Nagler's a guy who founded television. He designed his eyepieces. Some people swear by them. When they say type 5, type 6, that's to do with the field of view and the construction of the elements, the way it's designed. So some Naglers have a wider field of view. They might be type 6, another one will be a type 5. So 3 eyepieces will be type 4, another 3 will be type 5. And they'll all be Naglers, but they've got a different field of view and different construction. So that's all that is. I don't know about this purging on it. You know anything about that at all, Stefan? Because purging or anyone?
You'll get rid of the moisture in it.
They remove, they create a near vacuum inside, they fill the lens,
And put the
create a
gas.
near vacuum inside, and then fill that with nitrogen.
Oh, okay.
And that's sealed in, so you've essentially got, and that
Same as in the Nikon binoculars.
significantly reduces viewing or any fungal and things.
And they cost a fortune.
Similar thing in rifle scopes, a lot of them use argon.
Yeah, well that's what these are. The Explore Scientific use argon. They reckon it's better than nitrogen. But anyway, so if you buy Swarovski binoculars, which are $4,000 each, the top of the line ones are all nitrogen purged, and they cost a mint. And you don't necessarily. Anyway, the Bata Hyperion aspherical, that's the one I've got here. That one there. The 1 1/4 or 2, because look, it's got a 2-inch thing, but I can unscrew that, it's modular, and I can put a field stop on there that's 1 1/4. And I can use it as a 1 1/4 eyepiece. So some eyepieces are really good like that. And I haven't mentioned anything in here about zoom eyepieces. I've not even touched the subject. But you can get them. But, just like a zoom lens, they won't be as good as a fixed focal length. They can't be. Because the optical acrobatics involved in giving a range of different focal lengths just stands to reason. It's the same as with lenses. You get a zoom lens from 70 to 200, and you get a 200mm focal or fixed focal length lens. The 200mm fixed focal lens will kill the 70 to 200 at that focal length, at the 200, because the optical thing is superior for fixed focal length. It doesn't have to go through all that bending the light. And also, the more glass you've got, what happens? More light scatter, less contrast, etc., etc., etc. Okay, I'll skip through this because, anyway, I just talks about using different eyepieces on refractors and reflectors. The only thing is, if you've got a 2-inch, I've got a 2-inch diagonal, the mirror that you put the eyepiece into. When they come with those, you get a 1 1/4 inch adapter. So you can put a 1 1/4 inch adapter into a mirror, a 2-inch mirror, but you can't put do the reverse. You can't put, if you've only got a 1 1/4 inch mirror, you can't put a 2 inch eyepiece into it. Not that that's a great loss, because most eyepieces are still 1 1/4 rather than 2. Sorry, I'll speed up. They're the barrel sizes. Look at all the barrel sizes. The top one was early times, 1 1/4 and 2 are the most common. They even go up to 3 and 4. That's the size of my telescope. A 4 inch eyepiece.
They got a 3 or a 4 inch eyepiece for the discrete tier telescope.
Yeah, so big telescopes, big eyepieces. But other than that, no, you wouldn't see it. Anyway, we'll skip through that. So just quickly, I'm going to, I just talked about that, so I won't go over it. There's probably no real advantage in getting 1 1/4, smaller and lighter, less expensive, more choices, 2 inch eyepieces like that, a large ocular, comfortable viewing, wide field, focal lengths in excess of 40 are available, but yeah, other than that, a lot of money if you're going to buy. It would cost a lot more to get a 2 inch over a 1 1/4. And they're just barrel types, different sizes. We won't go into that. Moving on. Now, a field stop is that bit of glass. We won't look at it again. Can you see that? It's just a thing that blocks off the light. Now, that is important if you get binocular viewers, bino viewers for your telescope. It's critical. The choice of eyepieces, if you're going to buy bino viewers, I'm looking into this myself because I'm interested in getting a pair. But if you get some, the field stop of the eyepieces you use is critical. Otherwise you get vignetting. If it's not the right size, you get a loss of light around the edges. Because bino viewers got prisms and they add more focal length and the light, you get a dimmer image. You use both eyes, but you get a dimmer image. So field stop does become important. Anyway, I'll just go past that. We've already discussed that really. Then there's a bit here about, here we go, we've done that, field stop. A couple of examples of what I just showed you. On the right, look at the difference in the wide and one with a narrow field stop, quite significant. Television anglers, I'll leave that too because we've covered it. And now I think eyepiece types. Now I won't go through the history of these types. This type, if you want to look into eyepiece types, and you go to this site here, handprint.com, it is astounding. That's an astounding website because it's really for students of optics. And it shows you, if you were just starting off in optics at uni and looking into this, you go to that website and it's got the construction of every single eyepiece you can imagine and the glass elements, the way they fit together. So if you're interested in that, handprint.com is really good. And that's where I've got a lot of this information. The different eyepieces, Galilean, Huygens, Kellner, monocentric, Ramsden. I remember these eyepieces. I had a Huygens. With my telescope, my first telescope.
Were really good.
Yeah, but 0.96, they're tiny, but they weren't bad. It's just I didn't know what I was doing. Anyway, look, there's a field of view. See how the early days are a narrow field of view, and gradually they developed in time. If you're interested in this history, you can look it up. I'm not going to draw on it. But when you get down here, Plossels are the most common eyepieces around today, with most telescopes down the bottom there. But the one that interested me was the orthoscopic above it, the two. Ernst Abbe worked for Zeiss, Carl Zeiss, and he designed the orthoscopic. So a bit of a genius, and so it's called the Abbe orthoscopic. Is yours an Abbe orthoscopic or a Koenig, the other one?
No, it's an Abbe, yes.
It's an Abbe. So these are superior at high magnification. They beat everything else. They're really good eyepieces. Planetary and lunar viewing. So that's what they're designed for. I could have just had that there, not all that other writing. But anyway, I was interested in this. So low distortion, achromatic field lens, so that's the design, convex and a flat piece. Anyway, you want to look that up on that website. It'll have all the glass there. It'll have diagrams of every kind of eyepiece. And finally, specialist eyepieces. Those who've got Takahashi's, their LE eyepieces are supposed to be very good. I know Richard Higby, if he was here, he'd be swearing by them. I think he's got an LE, Takahashi LE eyepiece. RKE is special design by Edmund Scientific. So some of these companies that sell telescopes have got their own proprietary designs. So 52 degrees, now we're getting to normal eyepiece focal, field of view. Nagler panoptic. Is the panoptic. You can put two 24 panoptics into a bino viewer and get a decent field of view because the field stops are right in the right place. I've been reading about these eyepieces, which ones to get, and I've decided that you'd have to get the Nagler, the Teleview ones. They're the best. You bung them in, but they cost a mint. They cost a mint. And it's a bit, they're very expensive, and to buy two, twice the money.
Hard to get.
And hard to get. Some of them are hard to get. There was one that was they stopped making, and Ed Ting said it was the best one they ever made at 26 mil, I think.
Frank Ford is.
No, the one they stopped. They stopped making. They used to have a 26, and it was a brilliant lens, a masterpiece. And now they made the 24s. But anyway, they're supposed to be good. And then down the bottom there was my these eyepieces, which are regarded as being very good. So I was fortunate because I bought these without knowing they were very good. And I bought them from a guy who was well, I wouldn't call him a crook, but he sold me my big telescope. Eugene had some dealings with him of late. And he sold me these. He said, I got a set of these and they're the best. And after reading reviews, I realised, oh, well, they were. He wasn't trying to sue me. They are very good eyepieces. But there are others around too. So you've got to shop around. Anyway, the Barlow and the Park. Now, I'm going to summarise this. Barlow doubles or triples your magnification. Yeah. And so what happens is you're getting an increased focal length, but again, you're getting a dimmer image. You've got to think about that. But if you've only got 3 eyepieces, a Barlow can be a handy thing to have. If you don't want to buy any more, just buy the one thing. Then you've got 6 eyepieces instead of 3, effectively. Yeah. So
the other advantage is it keeps the eye relief the same as the eye.
Yeah, it's constant. So other things don't change. So it's really good from that point of view. There are different kinds. I think the best reviews are of the Teleview 2x Barlow. I've got one at home, sitting in a box, unused. And I mean literally unused. I've never used it because I've got a full range of eyepieces. But I bought it for one thing only. It screws apart and it fits into your optical imaging train, and then you get double magnification with your imaging train with a high quality glass in the way.
Most people is useful for planetary imaging.
Yeah, so that's what I'm going to use for later on. So it's not a waste of money at the moment. Or it is at the moment, but it won't be later on. So there's a handy thing. So you get 2 times, 3 times, but here realistically, if you magnify, you're going to get a degraded image, and it's going to be beyond the seeing conditions, everything else. There's not much point. There it is there. So you can unscrew that, the version I've got. Tell you 2 times Barlow. Now the paracore. Now, this is interesting. A universal corrector that tightens and intensifies star images of all F ratios down to F3. Because what it says it eats coma. Now coma is that aberration you get on the edge of your telescope. Say you've got a really fast telescope, a fast mirror, say in F4, it's going to distort, the star's going to distort. You use this eyepiece, you use this thing, you put your eyepiece into it and it compensates for that distortion. So it's got a, I'll show you, there's a picture of one here. There it is. That's a Teleview Parkour. So that compensates, sorry, so that compensates for that kind of distortion created by the optical system. I don't know how much they are.
Quite a bit.
Quite a bit, I would say. If they're coming from Teleview, they would be too. We're near the end. I'm going to stop in a minute. So the Barlow, this is the design of the Barlow, showing what it does. It saves space, increases, saves money on eyepieces, and maintains, as Stefan said, it maintains eye relief. You don't lose any eye relief by getting that extra magnification. Cons, darker image, increased possibility of optical aberrations, harder to track objects, less suitable for deep space, which is probably, depends. As long as you've got good tracking, they're probably fine. Now, I was going to talk about parfocals. Parfocals is just an aspect of lenses. You know, if you're a lens designer, you design a batch of lenses, and you design them in such a way that whoever's using them doesn't have to keep racking in and out and trying to find focus with every eyepiece of different focal length. So I actually find that these are not parfocal. I have to keep moving them a little bit each time, but I still have to move them.
Never found two that are parfocal.
Yeah, I think it's very hard to achieve. My
LBW says.
Yeah. So the Vixens.
Lenses, you have to adjust the focus.
Yeah, the Vixens are like that, which is a great advantage because you take one eyepiece out and put the other one in. Now, I'll tell you something, when I use this on Big Bertha, I have to use an extension tube to focus that 31mm eyepiece. I have to use a 2-inch draw tube. It will not come to focus, even on Big Bertha, which has got a massive range, but it won't. So I have to use that tube. If I take the tube off, all the others, the diagonal, work with the diagonal, but not this one eyepiece. So it's just so you can see the optical configuration makes a difference, doesn't it? Depending on what the eyepiece is. They don't all work the same way. So eyepieces, ideally in an ideal world, if they're all parfocal, wonderful. Par meaning even focus, so you don't have to keep changing, racking in and out all the time. There are some Vixen parfocal eyepieces. So Vixen make beautiful stuff. So, and there are parfocal rings you can attach to make your eyepieces parfocal, if you want to. But being an impractical person, I don't even bother. So we're near the end now, folks. So what does all this mean? I made up a little, regardless of telescope you're using, shorter focal length of the eyepiece, high magnification, more detail, fainter imaging versus square law, narrower true field of view, smaller exit pupil, less eye relief. Generally, not always, but generally. And then I've got some examples of eyepieces. And then the longer the focal length of the eyepiece, low magnification, less detail, brighter image, wider true field of view, bigger exit pupil, more eye relief. And then I've got them, I'll just give you some examples of wide field. Yeah, so there you go. And then super wide field, the latest one I think is about 110 degrees, 120 degrees. Apparent field of view of the eyepiece. And there are some examples of magnifications of different sizes. Pentax 104, what you can see of different magnifications. I'm sorry I'm talking through this, but near the end. So, yeah, there's a 31 through this is all through my small refractor. You can see how small the moon is. So it's about 1/6 of that field at 22, because the moon is 30.5. So 6 times half, it's about 3 degrees. That's a 3-degree field of view. Just there. Yeah. So, and up here, it's much, 100 magnification, it's a lot less, obviously. And different, here's the Eagle Nebula, seen at different focal lengths, you know, with the Hyperion, lowest magnification. But you see, what this doesn't show you is the brightness. So it's a fake illustration in a way. It's only designed to show the field. But if you're looking at it, the brightest picture would be in that one, almost certainly. You know, it is a smaller image but brighter. The magnified image will be give you, you know, the pillars of creation here, but you would have you know, it'll be a darker thing. So there you go. Examples of this. This is my whole set with low, medium, and high power. Choosing eyepieces. I just think you experiment basically. As long as you have one of each, a low, a medium, and a high. You know, somewhere in the range. You know, 42 or 30, down to 20, they're sort of low, and then in the middle you've got a 14 or a 10, and then the high ones are 7 and 5, things like that, smaller numbers. So, Richard's eyepiece collection. So, yeah, I was mucking around with it. I obviously had too much time to waste. Anyway, so choosing eyepieces, someone made up a table and I bunged a few things in there, but really I think the golden rule is to choose the eyepieces that suits the night, the telescope, and you just go through and you see what suits you most of all. I like a bright image. I'm not particularly fussed about high magnification, so unless I'm looking at a planet or something, then it makes a... Here are some examples of the expensive eyepieces. So you ask yourself, what's my budget? What diameter eyepieces will my telescope take? What focal length? What apparent field of view and eye direction do I want? And how will my telescope's focal ratio affect my purchase? So if you've got a fast telescope, f5, that's going to affect which eyepiece is used for it too. Because that's wide field. So premium eyepieces anywhere between $450 and $1,200. But they're not all, these are good ones. But then the same manufacturers make middle range ones which are very good, and you'll be strapped to tell the difference, quite frankly, with a lot of them. And then occasionally you get gems in the budget range, 75 to 200. You don't discount them just because they're cheap. Anyway, Fujiyama Ortho. I was thinking of you, Steve. Fujiyama. Have you had any experience with those?
No.
Yeah. Someone said they're really good. I read somewhere, and they're not expensive, so you can pick up some really good ones. It just shows you look at all the glass in those eyepieces. So that affects, that creates light scatter and loss of contrast too. The more glass you've got in them. And there's a bit about different eyepieces. We won't dwell on that. I think we're near the end now. Final thing, maintenance. Look, I reckon the golden rule is don't do what I saw one guy do on YouTube. There was do you watch The Angry Photographer? The Angry Photographer talked about a guy, and I saw the link. And this guy was demonstrating how, don't worry about, he had I think he had a camera lens, not an eyepiece. He said, nothing wrong with that. Look, easy to clean. You just, and this, and he wipes it clean. And the thing is, your breath's got acid in it, your saliva's got acid in it, and you might think your eyepiece is clean, but do that often enough, and you'll corrode the coating that's on those lenses. So you never do that.
Well, you're also putting a medium on it for things to live in.
Yeah, that's right. So important rule. First, do no harm. I like that. The Hippocratic Oath. Yeah, I wouldn't actually bother. I use little Zeiss lens wipes you can buy them in packets. They don't even contain alcohol now, and you just blow a brush, and if it's clean, just give it a wipe in a circular motion, and then use those beautiful little microfiber that come with glass cases too. They're microfiber, so you can use those. Yeah, perfect. And you don't need to. So I wouldn't worry about. I read somewhere there's this marvelous quote by a guy. He's sort of doing this sucking air, not blowing it, but sucking air across. I still wouldn't do that.
Come on.
I can't see the purpose of that. Then you just
You've left out the little lines of white stuff.
Yeah. I mean, just get a little blower brush. You don't need to do stuff. And don't ever use those spray ones, the compressed air, because they leak sometimes and they shoot that propellant out instead of air. And then it's good night, Irene, because your eyepieces have got the stuff on them that'll corrode the coating.
As long as you keep them upright,
you should. Right. Yeah, that's right. No tilting. That's another thing. Hold your eyepiece like this.
And test squirt first, just in case there is some fluid in the...
Yeah. Look at this. Dirt happens. This is a quote. I love this. And in moderate amounts, it has amazing little effect on performance. In his book, Star Testing Astronomical Telescopes, Harold Richard Suter analysed the effect of dirty telescope optics. Now, I'm obsessed with it because I look at my telescope and see a couple of spots. Telescope optics in full mathematical detail. His conclusion: the maximum amount of dirt that a perfectionist should tolerate on the telescope optics is about 1/1000th of the surface area. The size of a single obstruction about 1/30th of the diameter. So, in other words, on a 10-inch diameter telescope mirror, you can have as much dirt as in a completely opaque blot, 1/3 of an inch across, which is a lot. It's a lot. So that's quite a lot of crud to have no effect at all. And that's why I won't bother cleaning ever. I've seen really dirty optics, and you wouldn't know there was anything there.
One time you should check them though is my experience after public open nights, or when you're having public or other people looking through your telescope, you'd be surprised how often eyelashes will put oil on them.
And mascara.
For the women, but also children will grab your eyepiece and a finger will go on it.
Yeah, that's right. Yeah. I do that. I put a light on and I look at them all and use the old Zeiss ones.
Definitely check them after.
Yeah. Good point.
So rub your mascara off.
The mascara. Thank God no one wears coal anymore like they did mention it. Well, at least they don't out our way. Anyway, 10 steps to clean. I'm not going to go into that. It was basically summarising. And that's the last picture here. Not covered in this presentation, distortions in eyepieces. And these happen in telescopes everywhere. These are common things. But really, most eyepieces cope pretty well. If you look towards the edge of a wide-angle eyepiece, it's going to make you look sick. You're going to feel sick if you look at it, because it's like it's like the stars become a little bit distorted on the edge. But this one is very good at not doing that. The Hyperion, it's really good. I'm very pleased with it.
A quick question, going back to maintenance, I guess, in a way.
Yeah.
Buying second-hand eyepieces, is there any reason not to do that, or something you should?
No, I would just look.
Something you should be looking at doing when you're doing that.
I would, but I'd love to check the eyepiece out and see that it hasn't got anything done to it. There's by the way, I wish I could click on this. This is fantastic. In cloudy nights, there is a massive eyepiece guide, the biggest thing I've ever seen. It's an Excel spreadsheet, and it's got absolutely every eyepiece known to man on it. And all the configurations, and I think from memory it had prices. I couldn't include it here, but anyway, let's have a break. Yeah, so sorry about that. Boy, that's long enough. The other things, thankfully, are very short, extremely short, only 7 slides. Right? Why don't we have a little break? Yeah, thank you, everyone. So,
Thank you. All bought second hand.
Thanks very much, Richard.
Oh, that's all right. Not at all fair.
So all of those are free samples, right?
Yeah, sorry? The free samples, yeah, that's what I was just saying. Yeah, this is
I'm Mike.
Hi, Mike. How are you?
How was your trip to America before you came here?
That's America. Yeah, we're talking about down the west coast of South America, and then we're starting
Did you travel before you came to last time?
Stefan did.
Hi, I'm Mike. How are you doing?
Yeah, I remember you anyway. But we talked travel. Yeah.
Good, I'm actually driving on my own. Somehow I got into my navigation. So I was tonight. And I realized, oops, not the right place.
Yeah, that's all right for Friday. It's a couple days early.
It's not like, I wouldn't even have the car on Friday, so it's
all right. Okay. So you want to go and get out there anyway?
I mean, Barter had got a good
no, but it was funny, it's like,
and some of them are just that.
I'm not in the right place. So that's why I kind of slumped in.
Right.
A little walk of shame. How are you doing?
Yeah, I'm doing okay. Just had a week away with a friend. He's got things. He's up in December. So we're supposed to go camping with him up the East Coast. So he used to like to go. And we spent the week camping. The idea was he was going to sleep overnight in the camp with his lady friend. But that not even happened. And that was a rain all week before that, so we couldn't have a fire outside. He used to like to sit around the camp.
Yeah, I've been interested.
We got up and did a big giant bit and we stored it. And one last night, not before. Yeah, not before.
Well, that's interesting. You said that to me if you get a chance. I'll be interested. that's,
Oh, yeah.
yeah, but I'm gonna go down.
No, I just went on the job. I'm glad you said that.
Oh, absolutely. Oh, yeah. Yeah, it's like people that go to the funeral, you know, any funeral all the time. I mean, as I said, yeah, you want to see them.
Well, it's a different purpose for a different purpose.
Yeah, that's right. And that would be night sky.
A little bit. Still trying to get it. There's so much going on right now.
Oh, yeah.
But I did.
But I've got to do what I did. When I started looking at stars, I had to pick one constellation
Yes.
and then I went around. Yeah, we're trying to figure out what
Yeah, thanks for
constellation we've got right.
Well,
Well, that's okay, because that's one
and then you've got for $1,000.
You don't get the same list. I mean, it's obvious. I think that's in your last one we were talking.
Yeah,
because the sword goes up, so it's like a hammer. You obviously the sword's going the wrong way.
And
Judy's gonna have to be the opposite. That's something about that
what's the
today.
focal length of telescope? Is it 10 inches and probably about 800 mils, 1,000 mils? Well, I did a medium power eyepiece, like 10, somewhere between 10 and 14 mils.
Oh, yes.
And I reckon
Oh gosh.
you don't get any wide, you don't need to
There's
be
yeah, so most
because you've got a
people
wide field of error, you don't need a wide field of error.
Oh, okay, yeah. It's really a fascinating book.
I don't know if you've
I've said
Subaru cars. Their symbol is
Yes, yeah, I love that.
yeah, and I think it's only got 6 on it.
I don't know.
Yes. Next time you see one, get the city.
Yeah,
they're brilliant.
Yeah,
we don't have applications in Australia. I found application useless.
They say the galaxy, our galaxy, as Emu.
yes.
And sometimes I've never actually outside gone. When I've seen some images of people do that.
Yeah, get yourself, I'd say, somewhere between a 10 and
Right.
But yeah,
the Texas will be 4 to 500.
I've looked at
A good export scientific, good eyepieces.
I've looked at
They'll be
it.
in the same
I
range.
can't
Teleview,
recall,
same range.
or even say.
If you want to read a book, but it's worth it. I mean, you're going to keep it.
But then
Well, you do. They don't wear out, do they? I mean, so you might as well invest. That's what I do. Which is why I still. Yeah, I think so. I think you need, 40 to 30, and I mean,
There's one that's sort of like a bit skewed.
Well, I like one of the stars. I did study that constellation before I even got here.
All right.
And one of the stars is which I don't drink, but I think it's hilarious.
Ah, right, okay.
It's like
I'd say
whoever
10 to 14 in that range. I would
But it's
have
beautiful.
bought 7 in one piece.
Yeah,
Okay, that's all the way around.
turning things all that.
Yeah, absolutely.
Let's go for drinks.
Yes. These do me. Most nights I love the different films that you do. They all rate it 10 mil plus and say it's the best, but I reckon it's the seven. Pentax seven. Beautiful.
It's obviously
My Steve's on there. Don't know what it is.
they get the bail out and they thought, oh, this would be a great place to be on.
Yeah, they're cheap.
Tony was going to do.
I think they're Steve, Sorry, I say about
So he puts his telescope out on rock rolls. He has it set on his driveway for sets it all up remotely and then sits it on the laptop.
That sounds like a great way to do it.
Yeah, so
And there's the winery.
probably there are new ones.
Well, that's one of the things that I was like, okay, no stars, no lights, and I saw the word water.
Winery, yeah,
I said, I am talking the wrong place, I pulled right over.
So we can
Like that, find a place. It's hard to find a place, pull over when you want to.
you'll have a list of the sources here.
Because there's a few actually white close down.
Yeah, I think we can work out a way to get to that.